Hello, this session we shall begin by discussing the power of a lens. The power of a lens is actually the ability of the lens to converge or diverge a beam of light, and it is measured as the reciprocal of the focal length expressed in meters. So the ability of a lens to focus, to converge or diverge a beam of light is called power, and it is the reciprocal of the focal length expressed in meters. So 1 by f, where f is in meters. This is the power. So you know that converging lens, there are converging lens, converging mirror, diverging lens and diverging mirrors. So both the concave mirror and convex lens are of converging type, and convex mirror and concave lens are of diverging type. So this is the expression for the power of a lens. Now let us see how the effective focal length and power of two lenses can be calculated when they are kept in contact as shown in the figure, and also when they are kept at a small separation from each other. So here we have two convex lenses of focal length f1 and f2 which are kept in contact. Then the effective focal length of this combination will be 1 by f equal to 1 by f1 plus 1 by f2. So from this formula it is very clear that the effective focal length is smaller than the effective focal length of the combination is less than the individual focal lengths. So this is how, using this formula, we can calculate the effective focal length when the lenses are kept in contact. Now let us see how to calculate the effective focal length of two lenses which are separated by a small distance d. Here the formula for the effective focal length is 1 by f equal to 1 by f1 plus 1 by f2 minus d by f1 f2. So this is the formula when the two lenses are separated by a small distance d. Now suppose we put t equal to f1 plus f2. Suppose the separation between the two lenses is equal to the sum of their focal lengths. Then from the given formula, 1 by f will be equal to 0 or f will be equal to infinity. This means that the system will be neither converging nor diverging. So if the two lenses are separated by a distance equal to the sum of their focal lengths, the combination will be neither converging or nor diverging. So a parallel beam of light entering into the first lens will go parallel after emerging from the second lens. Now let us write down the formula that we have just now seen for the effective focal length of two lenses in contact and separated by a small distance. So when the lenses are in contact and of similar nature, the formula will be 1 by f equal to 1 by f1 plus 1 by f2. And when they are not of similar nature, that is, one is converging and the other is diverging, the formula will be 1 by f equal to 1 by f1 minus 1 by f2. Similarly, the formula for the effective power will be p equal to p1 plus p2, and here it will be p equal to p1 minus p2. Now when the lenses are separated by a small distance, the formula will be 1 by f equal to 1 by f1 plus 1 by f2 minus d by f1 f2. Remember, this formula is valid only if the incident beam is a parallel beam of light. Only for a parallel incident beam this formula can be applied. And here for the formula for the effective power can be written as p equal to p1 plus p2 minus d into p1 p2. So these are the formulae for calculating the effective focal length and hence the power of a system of two lenses when they are kept in contact and also when they are separated by a small distance. Now we shall discuss a defect of the lens called a chromatic aberration. So this defect of the lens is called a chromatic aberration. Now what is meant by chromatic aberration? See, if an object is placed in front of a convex lens, and this is a convex lens, and I have placed a point object on the principal axis of the lens, and a white beam of light emerging from the lens after passing through it, the image appears to be colored, and also Not only that image is colored, but the different colors are focused at different points. So the inability of the lens to focus all colors to a single point is called a chromatic aberration. Now let us see how this happens. We know that lambda r is greater than lambda v and nr is less than nv. So the refractive index of the red color is less than that of violet color, and from the lens maker's formula 1 by f equal to n minus 1 into 1 by r1 minus 1 by r2, we find that n for red is minimum. So when n for red is minimum, nr minus 1 will be minimum and 1 by f will be minimum for red color and f will be maximum for red. So fr will be greater than fe. Since 1 by f is minimum for red, f will be maximum for red. So the red color will focus at the farthest point. This is the focal point for red color and this is the focal point for violet color. And this is the focal length for violet and this is the focal length for red. So all other colors will be focused in between these 2 points. So this defect is called a chromatic aberration. This is actually the inability of the lens to focus all colors to a single point. Then this distance fr minus fe is a measure of longitudinal chromatic aberration. So the distance fr minus fe is a measure of longitudinal chromatic aberration, and this is df fr minus fe, and fr plus fe by 2 is the mean focal length. So fr plus fe by 2 is the mean focal length. Fr minus fe is a measure of longitudinal chromatic aberration and fr plus fe by 2 is the mean focal length. Then the ratio of the two, that is fr minus fe and fr plus fe by 2, or df by f. This is called dispersive power of the material of the lens with a negative sign. So minus df by s, that is called the dispersive power of the material of the lens. Now we have seen that the dispersive power of the material of the lens is omega equal to minus df by f and df equal to minus omega f. So df is a measure of the longitudinal chromatic aberration, as I have said earlier. Now for a single lens, you know that neither omega nor f can be 0. So you cannot have a single lens that is free from chromatic aberration. So if you take a single lens, whether it is a convex lens or a concave lens, you cannot have it free from the defect chromatic aberration. So how we can have a lens or a combination of lenses that is free from chromatic aberration? We know that for the effective focal length 1 by f equal to 1 by f1 plus 1 by f2. This is the formula for the effective focal length when the two lenses are kept in contact. Let us take differentials on both sides. So minus df by f square is equal to minus df1 by f1 square plus minus df2 by f2 square. Now we shall rewrite this. Here df is the longitudinal chromatic aberration which we would like to be 0. Therefore the left hand side is 0, or we will write df by f1 square plus df by f2 square, df1 by f1 square plus df2 by f2 square equal to 0. Now this is df1, or we will put the negative sign here itself, minus df1 by f1 into 1 by f1 plus minus df2 by f2 into 1 by f2 equal to 0. Now we know that minus df1 f by f is omega. So this can be written as omega 1 by f1 plus omega 2 by f2 equal to 0. So if you construct a lens, or we can multiply it as rearrange and cross multiply and rearrange it as omega 1 by f1 equal to minus omega 2 by f2, or omega 1 f2 equal to minus omega 2 f1. So if we can have a combination of two lenses made of different materials because different values for omega and of different types, one is converging and other is diverging, that is the negative sign indicates. As the negative sign indicates, one of the lenses is converging, another is diverging, made of different materials. Such a combination will be free from chromatic aberration. and that type of combination is called achromatic doublet or achromat. So achromatic combination of two lenses means the combination will be free from chromatic aberration. We have seen that a single lens cannot be free from chromatic aberration. Now how do we combine the lenses then? So I will draw a diagram showing how two lenses can be combined to produce no net chromatic aberration. So we have a convex lens of focal length f1 and material of the lens is having a dispersive power omega 1, and another lens, a concave lens, whose focal length is f2 and it has a dispersive power omega 2. Then this combination will act like a system that is free from chromatic aberration. According to our condition, one of the lenses should be converging, other should be diverging, and they should be made of different materials. Now let us do some problems which are based on the silvering of one surface of a prism and one side of a lens. So our first problem is about the silvering in the case of a prism. One face of a prism at an angle of 30 degree with the other is silvered. A ray falling on the second face at an angle of 60 degree retraces its path after reflection from the second face. Find the refractive index of the metal of the prism. So we have a prism of angle 30 degree and one face of this prism is silvered. And now it is further mentioned that a ray of light falling at the face that is not silvered at an angle 60 degree retraces its path after reflection from the silvered surface. So this is our incident ray. It is falling on the first face at an angle 60 degree. Then after passing through the lens, it hits the second face and retraces its path. So we have to find the refractive index of the metal of the prism. So we will write down whatever is given in the problem. Angle of the prism is 30 degree. Angle of incidence at the first face is 60 degree. These are the only two data that are given. Now let us see what happens at the second phase. It is mentioned that the ray of light after hitting the second phase retraces its path. You know that when a ray of light falls on a reflecting surface, it goes back to the first medium, or reflection takes place, and every time when a ray of light is reflected from any surface, we have to assume that the angle of incidence and the angle of reflection are the same. That is our first law of reflection, I equal to R. So even while drawing the ray diagrams, we must take into consideration the fact that angle of incidence is equal to angle of reflection. So here again we have to take into consideration that fact, angle of incidence is equal to angle of reflection. But the thing here is that not only they are equal, the angle of incidence is equal to the angle of reflection, the reflected ray follows exactly the same path as that of the incident ray but in the opposite direction. So the incident ray and reflected ray are traveling along the same line, not only in the opposite direction but along the same line. So the reflected ray must travel along the same line as that of the incident ray. For that to happen, the angle of the ray must be falling normally on the reflecting surface, because when the ray of light falls normally on the reflecting surface, the angle of incidence is 0. Then if it retraces its path, the angle of reflection is also 0. So we have met the condition, angle of incidence equal to angle of reflection, and the reflected ray travels along the same line as that of the incident ray. For that, both the angles of incidence and reflection are zeros. So at the second surface, R1, R2 equal to 0, and therefore I2 is also equal to 0. But we know that for a prism, A equal to R1 plus R2. So we have already, the angle of the prism is given 30, and the angle of incidence at the second surface we know which is equal to 0. So R1 plus 0. From this we will get R1 equal to 30 degree. Now we know that the Snell's law of refraction is given by n equal to sin I by sin R. So we can apply this Snell's law, sin I by sin R. I is 60 degree, R is 30 degree. So this we apply the Snell's law of refraction at the first surface. So this is sin I1 by sin R1. I1 is 60 degree, R1 is 30 degree. Therefore this will be sin 60 is root 3 by 2 and sin 30 is 1 by 2. So upon simplification we will get the refractive index of the metal of the prism as root 3. So this is how we find the refractive index of the metal of the prism in the case of a prism whose one surface is silvered. So our next problem is based on the silvering of one surface of a convex lens. So one surface of a convex lens, refractive index 3 by 2 is silvered. An object is placed at 20 cm from it. Then find the position of the final image. It's an convex lens because R1 equal to R2 equal to 10 cm. So this is our ray diagram. Here we have a lens, convex lens whose one surface is silvered, and this is the principal axis. So I have placed the object at a distance of 20 cm from the lens. It is immaterial whether the lens is placed at a distance of 20 cm from this surface or this surface, because in our syllabus we are dealing with thin lenses only. So it is enough that you mark the distance from the object to the lens as 20 cm. Then we have to find the position of the final image. So before proceeding with our calculation, let us see what happens here. This is our lens. Then a ray of light is entering into the lens. We have one surface of the lens silvered. So we will split it into two as a combination of a lens and a concave mirror. So the silvered lens now can be considered as a combination of a lens and a mirror. Then see what happens. The rays from the object will pass through the lens, they will hit the mirror, then they will return obeying the laws of reflection and finally emerge through the lens, producing the final image somewhere here. So this is our object and this is the image. So we find that after reflection from the mirror and then refraction from the lens, the final image is obtained on the principal axis. So this silver lens can be considered as a combination of a convex lens and a concave mirror. Now we have in order to find the position of the final image, we have to first find the effective focal length of this combination. Then using the formula law of distances, we can calculate the position of the final image. But first of all, our first objective is to find the effective focal length of this combination. Now how can we find the effective focal length of the combination? We know how to calculate the focal length of the lens and also the mirror. The thing here is that the ray first passes through the lens where it suffers refraction. Then it is the mirror where it suffers reflection. Again, while traveling back, it passes through the lens. So once again there is refraction. And finally you get the image on the principal axis. So you can consider this as a combination of two lenses and a mirror. And therefore the effective focal length will be 1 by F equal to 1 by FL plus 1 by FM plus 1 by FL. Now we have to put proper signs in this equation. You know that the final image is formed on the principal axis. The rays actually converge to a point on the principal axis, so that if I place a screen here, I will get the image in it. It means only one thing, the final image is real. The final image that you obtain in this case is a real image. And further, it is formed on the same side as that of the object. So the final image is formed because of reflection. So in the end, you get an image which is real and also on the same side as that of the object, and it can be formed only by reflection, and that too from by reflection from a concave mirror, because only a concave mirror produces a real image of a real object. Convex mirror produces real image of a virtual object, but here our object is real. So what we get in the end is a concave mirror, and we know that the focal length of the concave mirror is negative. So the final focal length is, equivalent focal length is going to be negative. Now we will separately calculate the focal length of the lens and the mirror. We will first calculate the focal length of the lens. Now it is given that mu equal to 3 by 2 and R1 equal to R2 equal to 10 centimeter. So we will write down the lens maker's formula. 1 by F equal to N2 by N1 minus 1 into 1 by R1 minus 1 by R2. Now N2 is the refractive index of the metal of the lens and N1 is the refractive index of the surrounding medium. So this is 3 by 2 by 1 minus 1 into 1 by 10. Then regarding the sign convention here, the incident rays assumed to be traveling along the positive direction of the x-axis from left to right, and all distances are measured from the center of the lens. Distances measured in the direction of the incident ray are positive and opposite are negative. So this is your first refracting surface and this is the second refracting surface. For the first refracting surface, the center of curvature is somewhere here. And for the second refracting surface, the center of curvature is somewhere here. So if you follow the sign convention, you will find that C1, which is the distance to the position of the center of curvature of the first refracting surface from the center of the lens, is positive, and C2, which is somewhere here, is going to be, and C2 is somewhere here, therefore R2 is going to be negative. So R1 is positive and R2 is negative. So this will be minus 1 by 10. So 3 by 2 minus 1 into 2 by 10. So this will be 1 by 2 into 2 by 10. So 1 by 10. Therefore focal length of the lens will be 10 centimeter. So we have obtained the focal length of the lens as 10 centimeter. Now what will be the focal length of the mirror? We know that this is a concave mirror and the focal length is R by 2. So focal length of the mirror is equal to radius of the curvature of the mirror by 2, and the radius of curvature is 10. So this is 10 by 2, which is 5 centimeter. So let us now substitute the values here. So this will be, what we get will be minus 1 by Fe equal to 1 by 10 minus of 1 by 5 minus 1 plus 1 by 10. Why minus? Because you have a concave mirror and the focal length of the concave mirror is negative. So upon simplifying this, we will get 10 as our LCM. So this will be 1 plus 2 plus 1. So this is 4 by 10 or 2 by 5. Therefore the equivalent focal length will be Fe equal to minus 5 by 2 centimeter. So that is our equivalent focal length. So the equivalent focal length of the combination is obtained as minus 5 by 2 centimeter. So now let us find the position of the final image. So in order to find the position of the final image, it is given that U equal to 20 centimeter. And according to our sign convention, we know that U is going to be negative. U is minus 20 centimeter. And the focal length of the mirror is minus 5 by 2 centimeter. So we have to find V. So let us write down the law of distances or the mirror equation. 1 by U plus 1 by V equal to 1 by F. So minus 1 by 2, and therefore 1 by V will be 1 by F minus 1 by U. This will be minus 5 by 1 by F is 1 by minus 5 by 2 minus 1 by minus 20. So this will be minus 2 by 5 plus 1 by 20. Upon simplification, 20 is the LCM. So 5 4 minus 8 plus 1. So minus 7 by 20, which means that our V will be, so upon simplification, we will get V as minus 20 by 7 centimeter. So that is going to be our V, which is the position of the final image.